Is it visible now? The whiteboard?
Yes, like that. Yeah, the whiteboard.
Okay, okay, good. So this is smart. $223. At one point in your life, have you done a course called basic mathematics? Basic mathematics. Okay, so then, which means then we are not going to struggle so much with you. So because the introduction is set, a business, okay, that's good. So how do we define a set? It's simply a group, as we say, not necessarily numbers, can be anything. Can be numbers, can be letters, can be people, can be whatever thing you want. So in simple terms, we say a set is any well-defined collection, or you can say group or a class of objects. Hello? Kidogo nito kuprint in class kidogo, sawa? Hello? In class kidogo nito kupranda mala. Sorry for that. So it's just any well-defined collection of objects. And then these objects are called elements of the set. Or you can say members of the set. Then the example you gave as a group of numbers. So numbers can actually be part of these objects, but not just numbers. We can also have letters. We can have names of people, cities, years, etc. So these objects can be numbers, letters, years, names, etc. So it can be anything. And then there are two main ways of denoting sets. Or you can say a set is specified by one, listing its elements. Inside a pair of braces. These are the kind of braces or brackets we refer to. And when you do this, this method is called roster method. I think this is the one, oh, so roster method. And then number 2, by means of a property of its elements. When we do this, we say we are describing the set by what is called set builder notation. So the general structure of set builder notation is so we write this to mean this read as the set of all elements X such that X has a property P. So for example, we can say the sets whose elements are the first 6 letters of the alphabet is written as, so you use this kind of brackets, A, B, C, D, E, F. So when I write this one, I'll be describing this set by what we call a roster method. If you want to describe it in the set builder notation, you will write set of all elements X such that X is English vowel, English letters. Can delete this. So that we describe X is a set of all elements such that X is one of the first 6 English letters. So if you are to write them, then we'll produce the same listing. So this is what we call the set builder notation. Then the second example, we can say the set of the even integers between 1 and 11 can be written as so what would be the numbers?
2,
2,
4,
4.
6, then and
Correct. So when you write in this form, we say that you have described it in cross-tag form. Then the same set can be written as set of all elements X such that X is an even integer between 1 and 11. So please note that when we are describing the property, we are using singular form, but then does not mean that the set will only be having one element. The definition of all these statements starts as the set of all elements X. So this is what this part means before you write the vertical line. So it means that you are going to list all of them which actually are obeying, or which each of them is obeying the property that you are providing. So it does not mean that it will only be having one element, because the definition of the description or the property comes out in singular form. Okay?
yes.
Yeah. And then when we can use this vertical line, the vertical line in the description of the set builder notation can also be replaced by colons. So vertical line or colons means such that. So in all these examples I've provided, where there's vertical line, you can as well put columns and it will have the same interpretation. For example, if I have another example number 3, then the set of the first 6 natural numbers is written as, so what would be the list of, what would be the elements in this set? 1, 2, 3, 4. 6 is part of that set, eh? Okay. Is it part of that or is not part of? Yeah, because we are saying the first 6. So by doing this, this will be roster method. Then I think that will still provide you the same set. Yeah. So there are many ways of describing a property for the elements. As some will have only one way of describing, but some will have different forms that will produce the same listing. So NB we usually use uppercase letters to name sets and lowercase letters to name elements in the set. So for example, this is what I mean. So I can say A is equals to R, A, E, O, U. So then this is A is a set of the English vowels. So that I'm giving the name to this listing as A. You can also have, say, I have a set B, 1, 2, 3, 4, 5, 6, 7. And then you can say B is a set of natural numbers less than 8. And then you can say, I have a set C, Eric, Jane, Agnes, 1, 2, A, X, Y. So that's another example of a set. So the key thing is that we are giving it the name C. We can say D is a set 1, 2, 3, star, alpha, A, B, X, W, 20, 28. So elements can be anything. So the key thing is that we are saying that instead of writing just the braces and then put the elements, then we can give one name to that listing by picking one of the capital letters in the alphabet. So notation and terminology. So we use the sign to mean an element of or a member of or belongs to. For example, if this is a set A, if that is a set A, then I can write that will mean that A is an element in set A, or A belongs to A, or A is a member of set A. You can also write 2, and that will mean 2 is an element in set A, or 2 belongs to A, or 2 is a member of A. You can also write that 3 is an element in set A. Now, what would be the meaning of this if I do this and I write this? Correct. That's the opposite of what the other sign means. So this means it's not an element of, or is not a member of, or does not belong to. So that's the meaning of that sign. So for instance, if you are considering this set A that we are given, then we can write, for example, C to mean that when you go to the list of this set A, you don't see an element named C. Or you can write which simply means that if you go to the list of these elements defined in set A, you don't find an element called D. You can also say 4 is not an element of set A. Or you can say Z is not an element of set A, etc. So I hope that notation should make sense for belonging to. Is that good?
Yeah.
Yeah. Then there's a term we call an empty set. So by the name itself, empty set will mean a set with no element or elements. So you say this is a set with no elements. For example, if I have a set, I call it A, and I say A is a set of all real numbers X, such that X you should see that that's an empty set. Are you able to recognize that? Do you see why? Yeah, because we are saying that A is a set having all elements X, such that X is a real number and X squared is less than 0. From your discussion of numbers, you know that there is no real number. When you square, you get a value that is negative. Okay? Yeah, so when you say that you are squaring a real number and you get a negative number, then that doesn't exist. There's no such kind of number, which will be real, and when you square, you get a negative number. Another example, you can say people taller than times towers. That should make sense. There is no normal human being whose height can be taller than times towers, a building which has more than 20 floors. You don't see such human beings don't exist. We can say C, balls which produce 10 liters of milk daily. That should also be an empty set. You can also give another example. Set of all elements X, such that X is a natural number. And 2X minus 3 is equals to 8. Can you explain why I'm calling that an empty set? Is equals to 8. If you are to solve that equation, what will be the value of X? Yeah, and you know 5.5 is not a natural number, okay? Yeah, so then when you say that X is already a natural number, then that really is like a contradiction in the first case. There's no natural number that when you replace here, in this place for X, left-hand side will give you positive 8. And just know that an empty set is usually denoted by this sign is called phi, or you write braces, but you don't put any element or any object within the braces. And probably, maybe I was supposed to tell you this from the start. You have to be very careful that the kind of brackets we use to define sets are these kind of brackets. You know, in English, there's this bracket, there's this other kind of bracket, and then there's this other kind of bracket. In English, there is nothing special. All of them are brackets. But here in this topic and generally in mathematics, every bracket has a special meaning. So when you are referring to sets, we mean this. If you replace those by this other kind of brackets, you get it wrong. So I hope what you are writing is correct. Okay. Yeah. Immediately you change now. If you write, for example, A, B, C, is not the same thing as writing A, B, C. This will mean set. This is just ordered triple of elements of values A, B, and C. So as you write, ensure that you write with the correct notation. There's what we call singleton set. So singleton set is a set with only one element. So from the name even itself, we can actually know what it defines. A singleton set is a set containing only one element. For example, if I have that set, it's an example of a singleton set. If I have this, is an example of a singleton set. If I have this, is another example of a singleton set. If I have cat, is another example of singleton set. If I have just A, is another example of a singleton set. But it only has exactly one. So that's what qualifies for set to be called singleton. So the other definition is what we call subset. So to define a subset, you require two sets. So you say let A and B be two sets. A is said to be a subset of A, a subset of B, if every element of A is an element of B. Denoted by so that is how we denote A is a subset of B. So if all elements of set A are elements of set B, then A is called a subset of B. And then before I give an example, I'll also define what we call proper subsets. Then I give an example to help you to distinguish between the two terms. So proper subset. So let A and B be two sets. A is said to be a proper subset of B if every element of A is an element of B and B has at least one element not in A. We denote this by what we denote by A being a proper subset of B. That every element of A must be an element of B. And also, B has an extra element, at least one element which is not in set A. So if I have, let A be this set, B be this set, say D, C be this set, D be this set, and E be this set. Right, those are they 5 sets? Then I want you to tell me from your understanding and what you have defined, what set can be described as being a subset of the other set. Yes. Just let's go one by one. Yes. B is a subset of A. Subset of E. So B is a subset of E. That's true because all the elements of B can be found in E. Okay. That's a true statement. Is a subset of. Also, A is a subset of E, correct? Because all the elements of A, which are A, B, C, are found here, A, B, C, correct? Any other relation? What did we say, proper set? or maybe to make us to make me now prompt your understanding and reasoning. Let me. I want to write, and you tell me whether it is true or false. True or false. Huh? I want to write a statement, and then you tell me whether, according to your understanding of proper subset and subset, whether it is true or false. When I write, is it true or it's false? Reason? Mm. Stick to the definition. Stick to the definition before you ask your question. Does it agree with the definition? If it agrees, then just you give me the answer. Then we'll discuss what you want, what you're asking. Does it qualify the definition you have given? It is true, because remember, we have said that a set A is a subset of a set B if all elements or every element of A is an element of B. Okay? So for you to know whether this is a true statement or not, just check. The first set is what actually helps you to know whether it is a subset of the second set or not a subset of the second set, by simply checking that all the elements of the first set can be seen or can be found in the second set. So for instance here, small a can be seen in C. Small b can also be seen in C. Small c can also be seen in C. So then it qualifies to be called A is a subset of C. Okay? Now, will it be true for me to say that A is a proper subset of C? Why? Why? Okay. So now you have said yes and you have said no. So now explain. Defend one of your answers. Mm. 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 But is it the case here? Yeah, so then now, this is not true. This is a false statement. Since no element in C is not in A. So remember, the condition for proper subset is that one, all the elements of the first set must be in the second set, all of them. Number two, then you have to check that that second set has extra element or elements that are not in the first set. So those are the two checks you do. That everything that is in the first set must be found in the second set. And then on top of that, show that this second set, there is at least one or two or three, or at least one of the elements which are not in the first set. So which is not the case for these two sets A and C. And will it be true for me to say that C is a subset of A?
Yes.
Because That's not how we reason. Remember, the order matters on how you are actually comparing. So when we write this one, you should start your argument with C, not A. You start your argument. You start your argument with the first set, not the second set. Correct. Yeah. So that's how that's the reason you give that all the elements in the first set are in the second set. So that is enough to show that the first set is a subset of the second set. So this is also true. And then is this statement true? If I say C is a subset of E, it is true because all the elements of C can be found in E, okay? Now, when I say C is a proper subset of E, true or false? Why? Yeah, so you get it correct. That the first, so there are two checks. Check that all the elements of the first set are in the second set, and then also see that the second set has at least one that cannot be found in the first set. So that is working for this case, okay? And then is it true for me to say that E is a subset of C? Why? E.g. Good. Yeah. So I see now you are mastering what's happening. So then this not be a true statement, okay? And that you can give that reason as to support that as a reason to support your answer. That E is not a subset of C because all the elements of C cannot be found in C. All the elements of E cannot be found in C. For instance, D is in E, but D is not in C. Okay. So now to describe, to make it now a true statement, you will write E is not a subset of C. So when now you draw the sign for subset and then you cross with a line, then that is read as not a subset of. I hope the concept of proper subset and subset is making sense to you. So if I may ask, is it true that when a set is a subset of another set, then it must be a proper subset of the other set? Let me write it and then you tell me whether it is true in general or not. So is it true in general that if A is a subset of B, then A is a proper subset of B? That is one, okay? And then two, A is a proper subset of B, then A is a subset of B. So I want you to tell me which of those two is true in general, or all of them are true, or all of them are false. Okay. Mm. 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 You can give an example. There's no even when you give an example, it makes your work. It makes even explanation better. You can support with an example. Mm. 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 So all of them are right. Okay. You are sure? Now let's go the first case. We are saying that if A is a subset of B, then A is a proper subset of B. So I want to determine whether it is always true in general, or there are cases where that statement is not true. Do you see, for example, set C and set A in our case? See, you are the one who told me that A is a subset of C. You are the one who gave me this answer. This answer, you are the one who told me. And you are the same person who gave me this answer. Yeah. So you see, that one is enough to help you answer what you want to answer. But when you say A is a subset of C, does not necessarily mean that A will be a proper subset of C. If you use that as an example. I don't know if you're able to see that. So saying that A is a subset of B is not a guarantee that it must be a proper subset of B. For example, in this case, A was a subset of C, but here we found that A is not a subset, is not a proper subset of C. So that's not always the case. A being a subset of B does not always mean that it will be a proper subset of B. But then, if you reverse it now, if you say A is a proper subset of B, you know, by the time you are saying that A is a proper subset of B, you have already tested the aspect of being subset. If you check your definition, because we say that A is said to be a proper subset of B if every element of A is an element of B and B has at least one element not in A. So that first condition in testing the proper subset is really what defines the subset. I want to see that. Yeah. And then now you go ahead and check that the second set has extra element or elements which are not in the first set. So by the time you conclude that A is a proper subset of B, it means that you have gone through all those two stages. Okay. So which means then it's enough to show that by the time you conclude that A is a proper subset of B, then it must be a subset of. Yeah, so it will always a subset, yes. Yeah. When A is a proper subset of B, as you say, it's already a subset of B. So then this second statement will be always true. So this is always true. But the first one is not always true. There are cases when it is true, there are cases when it's not true. Good. And then equal sets. So two sets, A and B, are equal if A is a subset of B and B is a subset of A, i.e., they contain exactly same elements. And we denote this by just the normal equal sign. So that is when we say that two sets A and B are equal, that they have exactly the same elements. For example, I can say if I have a set A, B, C, and the sets B, A, C, B, and the set C, C, A, B. All these are equal sets. And then to attention, always know this. Number one, that order does not matter when listing elements of a set. And then I'll explain with an example. For example, if I write A, or let's say 1, 2, 3, 4, it is the same thing as writing 2, 1, 3, 4. I'll be defining the same set as writing 4, 2, 1, 3. I'll be defining the same thing as writing 1, 2, 4, and then 3. That order does not really matter when you are listing elements of a set. Then note number 2. Repetition of elements in a set do not create new sets. This is really what I mean. For example, if I write 1, 2, 3, it will be the same set 1, 2, 2, 3. It will be the same set 1, 2, 1, 2, 3. It is the same set 2, 1, 3, 1, 2, 3. Remain the same set. That's to mean when I do repetition of elements, I'm not creating any new set. If those are the same sets I'm using, then I will be having the same elements I'm using, I'll be having the same set. Hello, Dr. Hello? 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 So that is not creation of any new element. Hello? I'm fine. Does that one make sense to you, my friend? Ask. Like what you have explained, what you are explaining here is that all these are examples of equal sets. Or maybe now ask a question. Repetition we mean that when I write an element, for example, twice, I don't now say that this set I'm writing has 4 elements, 1, 2, 3, 4. They remain to be 3 elements, 1, 2, and 3. By me writing 1, 2, 1, 2, 3, does not mean that now I've created a new set with 1, 2, 3, 4, 5 elements. It remains to be the same set with only 3 elements, 1, 2, and 3. I don't know if that is making sense to you. Yeah. So that now, the next thing is cardinality. So this is the number of distinct. The word distinct is very key. Elements contained in a set. The number of distinct elements contained in a set. For example, or for notational purpose, if I have set A, then let me try with this cardinality. For a set A, the cardinality of A is denoted by so you write A within 2 vertical lines, or you write N into A, or you write, so you can either write capital N or small n into A. All this means cardinality of set A, which simply means the number of distinct elements contained in the set A. So let's do an example. We'll say that. Find the cardinality of the following. So A, B, C, D, E, F, B, A, B, C, D, E, F, and then the other example is C, A, B, C, D, E, F, D, A, B, C, A, D, E, F, B. Those will be enough to make us understand what is happening. Or maybe let me add the last one. E, the empty set. F, 1, 2, 3, 4, 5, etc. So what is the number of distinct elements in set A? How many are there? There are 6. So we say the answer to A is that cardinality of A is equals to 6. Good. B. So let's see. 1. How did you get 4? Yes, that's really what I want you to help. Want you to explain to me. That's why I said that question. We have 2 sets. Still 6. You are sure? We have how many elements? Mm. Mm. Okay, so how did you enumerate the elements in the first set A? So you simply start by, so you are counting this A, the first one, comma, B, the second one, comma, C, the next one, comma, then up to F. So the elements are separated by commas, and it's also possible for you to, have sets within a set. And when sets are within a set, they are counted as elements of that set. They are not now count, you don't count now one by one. So here, this will be the first element, A, this is the second element, this is the third element. Now all this is counted as one element. And then this is the fifth element. So you don't count this as 2, it's counted as 1. So it is a small set which is counted as an element within set B. Is not a subset of B. It is an element in set B which happens to be a set. So then cardinality of this will be 5. So then now you should be able to tell me C without struggling. 4. So 1, this is 2, then 3, and then 4. So this will be 4. These are done? I've catched you. I've catched you. Do you know why I've catched you? Yeah, I think you are answering yourself. I'm happy that you are answering yourself. Hey, you are now even making it worse. So how many are they? Yeah, so remember, that's why I even underline this, underline the term distinct. So distinct is a key term in this definition. If you delete it, then it loses the meaning. So the elements in D are 6. And what is the cardinality of E? Empty set. Cardinality is 0. So, and actually you cannot get any, you can't write that the cardinality of a set is -2. It can never be negative. The smallest number it can be is 0, and is 0 when you are dealing with an empty set. And then cardinality of F, infinity, correct? Because this list now, when we have these 3 rows, it means that the numbers continues indefinitely, okay? Good. And if I had G, what will be the cardinality of G? 100. So this one you big, this one you know that there's an end, because you see they are telling you where you are stopping. And it's only that we cannot list all these numbers in between here, but you know the pattern, okay? Yeah. So in general, always, in general, for any set A, cardinality of A is always between 0 and infinity. And when cardinality of A is infinity, then A is called an infinite set. And so for finite sets mean that we'll have a fixed number for the elements within the set. So then another operation is what we call, before I define it, I want to kill 2 birds with 1 stone. Because you told me that you have already done this one in business mathematics. So the term Venn diagram or Venn diagrams is not new term to you. True or false? Yeah, correct. So Venn diagrams, these are simply pictorial representations of sets. And we usually use a rectangle to denote the universal set, which is usually called U, and circles are drawn within the rectangle to represent other sets under consideration. So rectangle is used to represent the universal sets, and then circles are drawn within this rectangle to represent other sets. Then if you remember, we defined, or you defined, a universal set. So universal set, usually denoted by this U, is a set that contains all elements under consideration. The set that contains all elements under consideration. It is also called the universe of discourse, or simply the universe. So let me ask a question. If I consider, say, set of men and women, okay? What would be the name for my universal set? So if I consider a set of men and women, then the possible universal set is a set of, it's like I'm asking you one word that can take care of men and women. Human beings, correct? Human beings. Or simply people. Then if I have number two, if we consider the set of cows, dogs, goats, say ducks, chicken, cats, then the possible universal set is domestic animals will work perfectly. It will take care of all these things we are giving the list. Or even when you say animals, it will still take care of what we are listing, okay? Yeah. So sometimes the universal set is not unique. So it's domestic animals or just animals. So in simple terms, to interpret the meaning of the universal set simply means that it is a bigger set that will take care of all the other smaller sets or elements you are considering. Maybe just last example, number 3. If I have this, say I have 1, 2, 3. I have 2, 4, 6. I have 1, 3, 5, 7. And I have 4, 6, 8, 10. For example, if I have these smaller sets, you can call this one A, you can call this one B, you can call this one C, you can call this one D. Then possible universal sets are, so remember the term universal set with respect to some small sets being considered is not unique. is simply what can take care of all the smaller sets, smaller elements which are being considered. For example, I can say, here I'll say the universal set is set of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Another person can say the universal set is 1, 2, 3, 4, 5, 6, 7, 8, 10. Another person can say the universal set here is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Or I can say 1, 2, 3, all the way up to even say 20. You let me know when we are done so that I explain what I mean here. Can I explain what I'm saying? Yeah. So here, if I call this one U1, this one U2, U3, U4, U1 qualifies to be called the universal set with respect to these sets A, B, C, D, because by one, for set A, it has elements 1, 2, 3. When I go to this list of U1, I'll see 1, 2, 3. So all the elements of set A are within this U1. I go to B, it has 2, 4, 6. I can see 2, I can see 4, I can see 6 in U1. So it has taken care of all the elements of B. I go to C, I have 1, 3, 5, 7. I can see 1, I can see 3, I can see 5, I can see 7. So all the elements of C are also taken care of in U1. Then D, 4, 6, 8, 10. 4, 6, 8, 10. All the elements of D are also taken care of in U1. So because in all the smaller sets A, B, C, D, all their elements are contained in U1, then U1 qualifies to be called the universal set with respect to the sets A, B, C, and D. And it is the same explanation for U2, U3, and U4, that if you go one by one to each of these smaller sets A, B, C, D, all the elements are taken care of in all these other listings. So the thing is that we don't care whether what we are calling the universal set has some elements which are not in any of the small sets we are considering. What matters is that all the elements within the small sets we are considering can be found in that other bigger set we are calling U. I don't know if that makes sense to you. Yeah, so that's what you have. So universal set is not unique. There are cases whereby same sets of same elements being considered, they have infinitely many possible universal sets. So so there's what we call complement of a set. Complement of a set. So to define complement of a set, you need to know the universal set, and then the complement of the set being considered will be simply the set of all elements which are not within the set that you're specifying. So in short, this I mean, let U be the universal set, and A be any set in U. So U is a universal set, the bigger set, and then we have, within this bigger set, we have a set we call A. So the complement of A is another set within U, denoted by A, you write A prime, or you write A power small c, or you can write A, then you put a bar on top of A. All those are the same notations, which is the set of all elements not in A, but in U. So if you want to be more technical or more mathematical, you can write this definition in set builder notation as A complement is a set of all elements X such that X is in the universal set, but X is not in the set A. So we're almost stopping. So to make it clear on what we mean, I'll draw a Venn diagram and then I shade the set that we call A complement. And then it will make your understanding much clearer. So you draw this. Believe that this is a rectangle. Believe that that's a rectangle, but please draw a better diagram than mine. Then draw an arbitrary circle to represent set A. Then you label this as U to mean universal set. Then within U, you draw that circle to mean set A. So how many regions are within the circle, within the rectangle? After drawing the circle, how many parts are within the rectangle? 2, correct. There's one part within the circle and the other part outside the circle, okay? So what we call A complement is this part which is outside the circle. And when you are shading, you ensure that your shades are close to each other and very uniform. Because at one point in time, we'll be using these shades to confirm that two sets are equal. So when you're shading, you try to be orderly. So don't just scribble. So then and remember when you are dealing with Venn diagrams, we usually shade the required set, okay? Yeah, so what is shaded is what we call a complement. So if someone can loosely ask you, what is complement of Dave? It's a funny example. If I ask you, what is the complement of the term Dave? What will be the answer? Night, correct. And loosely speaking, what will be the complement of the term boy? Girl. So that's really what we mean. So when they tell you to represent complement of a set in a Venn diagram, the first thing is that you need to know the region that defines the set. Okay? And then once you have known the region that defines the set within the Venn diagram, then you shade now what is not in that set, outside the set, within the rectangle. Okay? Good. And then if I have now this, let A be the set A, B, C, let B be the set C, D, E, and let C be the set A, B, C, D. And the inverse of set A, B, C, D, E, F, G. Then what will be the A complement? D, E, E, F, G. And remember, one thing that should be very clear, which is always true in general, is that whenever you take a set and it's, okay, I will define that one when we have defined another operation. So keep that one for now. I'll explain what I wanted to explain after defining another operation we call union. So then now, when you take the total number of elements in A complement plus those which are in A, you should get the same number in the inverse of set. So like A has 1, 2, 3. Complement, you're saying it has 1, 2, 3, 4. So 3 plus 4 is 7. And U is 1, 2, 3, 4, 5, 6, 7. So that must be true. And remember, we said when we are defining, we are saying the set of all. So when you don't list all the elements, then you don't score. And what would be B complement? You are sure? C is part of that set? F, G. Because remember, you cannot include D and C because they are in the set B itself, okay? So remember, set and its complement is like day and night. There is nothing in common. And then C complement. F, E, F, G. Correct. Then now, let's define what we call the union. of sets. Union of sets, we use this sign. Now is different from the universal set sign. So universal set sign, we usually draw U and then we put a small tail. But this one is just now U facing upwards without a tail, like capital U. So we'll say let A and B be two sets. The union of A and B is a set of all elements contained in A or in B or in both. We denote the union of A and B as so that's how we denote the union of A and B. That you pick all those elements in set A, or you pick all those elements in set B, or even pick what can as well be counted to be both in A and in B. So if you want to be technical or more mathematical, you can give this definition using set Euler notation as set of all elements X such that X is in A or X is in B or both. In fact, even if you delete the word or both, it will still be perfect definition. Even if I delete this, I still have the same interpretation. So note that as we'll be progressing by, we will be meeting this word or and the word and, both in this chapter and chapter on logic. So note that whenever you see a union, the defining term is the word or. So just keep in mind of that. Similarly, for three sets, A, B, and C, A union B union C is a set of all elements X such that X is in A or X is in B or X is in C. And you can give the same definition for even 4, 5, 6, up to n number of sets. And so you can say, in general, for n sets, A1, A2, A3, up to AN, A union A1 union A2, union A3, union up to union AN is a set of all elements X such that X is in A1 or X is in A2 or X is in A3 or X is in AN. So I want us to draw a Venn diagram to illustrate what we mean by A union B. So I'll have this as my universal set, U. And then I have, let me call this set A. And then let me have this as my set B. Okay. So the objective here is to represent or to shade A union B. So how many parts can you see within the rectangle after drawing those two circles A and B? 4 parts. There's this part outside, there's this part within A, there's this part common to A and B, there's this part 4. So with what I've defined, where should you be sitting or standing to be counted to be in A union B? Part 3. Or let's go back to the definition. So this is the definition. A and B are two sets. The union of A and B is a set of all elements, contained in A or in B or in both. I assume you know the meaning of the term or. So let's go now back to the diagram as we have requested. So this is the diagram. So where should we be sitting to be counted to be in A or in B? All the circles. So in terms of parts, we mean part or parts. Correct. You are going to shade, as we just said, everything within the all the parts within the rectangle, within the circles, is what will be defining that set. So remember, you don't have to write those numbers 1, 2, 3, 1, 2, 3. Yeah, I was just drawing them or writing them for illustrative purpose. It's not part of the solution. I just labeled 1, 2, 3 for you to tell me how many parts. So that's what. So that's the set we call A union B. And then for 3 sets, let's also draw. So this is the inverse of set. So if this is set A, I have this as my set B. And then I have this as my set C. Please, unless there's enough information in the problem that there is no part where the circles are touching each other, you must always draw them touching each other this way. Okay? Yeah, you only separate them if there's clear information that they are not touching each other. But by default, we always draw them touching each other. So if I label this as 1, 2, 3, 4, 5, 6, 7, 8, which part will be defining A union B union C? Part 2, 2, 3, 4. 2, 3, 4, 8, 7, and 6. Okay, let me make your life easier. We said A union B union C means elements which are in A, or which are in B, or which are in C. So from this diagram, A is which circle? In terms of color, black circle, okay? So if you say you are in A, you need to take care of all the everything within the black circle, which is 2, 3, 4, 5. And then, or B. B, you need, which color is that? Is that blue? So 4, 5, 6, and 7, okay? And, or in C. C is like what looks like pink. 3, 5, 7, 8. So then now, A or in B or in C. So we shade. So in simple terms, you shade everything within the circles, okay? So you shade all parts within the circles. So that is what we define A union B union C. And if I have now A is the set 1, 2, 3, B the set 2, 4, 8, and C the set A, B, 1, 3, 8. What will be A union B? What elements will form A union B? Yes. Correct. So remember, 1, 2, you don't have to repeat writing 2 because it has already been written. Repeating does not create anything new, okay? Because it means that we are going to take everything that is in the first set, join to what is in the second set, okay? Yeah. And what will be A union C. And 8, correct. And then A union B union C. 1, 2, 3, 4, 8. AB. Please remember that you shouldn't be scared, even if you write 8 and then you write 4. We said order does not matter when you're listing the elements. You still be perfect. So you don't have to say that now when from 1, 2, 3, I must write them 1, 2, 3. You can even start with 3, 2, 1. They still be fine if you are listing elements of the set. But please don't misquote me to say that now everything we discuss on sets order does not matter. We'll see other operations whereby order matters. So what I'm explaining about the order in this at this stage is that when you are listing elements within a set, that's where order does not matter. You're allowed to do whatever you want, provided you list all of them. But there are some other special set operations where order will matter. Okay. Yeah. Then lastly, for today, the intersection of sets. So intersection, we reverse the sign of union. And we define this as let A and B be two sets. The intersection of A and B is a set of all elements contained in both A and B. We denote the intersection of A and B as and just the same way we did for the union, you can provide this definition in more compact form as set of all elements X such that X is in A and X is in B. So the main term in this operation is the term and. And then similarly, for three sets A, B, and C, the intersection will be the set which has all elements X which are in A, and those elements are also in B, and those elements are also in C. So the governing word on the definition of intersection is the term and. So you must be in both A and B if you are having two sets. If you're having three sets, you must also be common to all of them. So if I have to draw a Venn diagram, I call this set A, I call this set B, you don't have to put in your diagram the numbers, but me, I want to put them to enable me explain. 1, 2, 3, 4. So what parts should I shape to represent what I've given the definition? A intersect B. I think that should be obvious. Huh? Yeah, that 3 is where the red circle, which is A, meets the blue circle, B. And that is in line with the definition of the intersection operation, the set of all elements which are common to the sets A and B. So you shade this. Then let's draw a diagram for 3 sets. So this is the universal set. So I'll have that. I'll have this as my A. I have this as my B. I have this as my C. So 1, 2, 3, 4, 5, 6, 7, 8. Are you able to know where we are going to shade to represent A intersect B intersect C? So remember, A intersect B intersect C means you are in A at the same time you are in B, at the same time you are in C. X is in A and is in B and is in C. Six is the only part that will be common to all the 3 circles, okay? Yeah, so 5 is not in all the circles because if where the location of 5 is, the pink circle is not there. Like this. So this is the part. So this is the part here. So we can stop at that point and then next time we'll pick it from there. Okay, that's it. Have a good evening. Eh? Okay.